So this session is a session on the special track of applications, and this first talk is going to be on planning personalized museum visits, and Stéphanie Roussel is going to present the talk. Thank you, Stéphanie.
Hi, so I still don't know how I'm going to go to the next slide, so until then, so my name is Stéphanie Roussel, and I will present you some joint work. Yeah, okay, but how can I...
There should be a remote control.
Okay. So until we find the remote control, so I'm going to present you some joint work that has been realized with Daniel Lebert and Pierre Marquis. And the three of us are from CRIL, which is the center of le Centre de Recherche en Informatique de Lens in North France. Okay. So this is the next slide. And so the work I'm going to present is about planning personalized museum visits. Okay, so the problem is the following one. Let's take a couple of tourists that want to visit some museum in the city, and they have some preferences about what they want to see. So, for example, they really love Leonardo da Vinci paintings. They kind of like Matisse paintings, but they don't like at all contemporary paintings. So these are their preferences. Those visitors can have some constraints too. So, for example, they do not want to spend more than 2 hours in a museum. So this is the duration of the tour constraint. Then they might want to include or to exclude some specific artwork in their visit. And they can have as well some specific topology constraints. So, for example, if a visitor cannot take the stairs, then the topology of the museum won't be the same for it. And the problem is the following one. Given the preferences and the constraints of the visitor, our goal is to compute the tour that best matches the user requirements. So why is this application novel? So if you go on the website or on the websites of any big museum, you will have a set of predefined tours that are proposed to you. The thing with these tours is that most of the time they do not correspond exactly to your preferences. So there is a mismatch of preferences between what you really want to see and the tours that are proposed to you. Second thing is that most of the time predefined tours are very long, and if you do not want to spend a lot of time in the museum, then your duration constraint is not satisfied. And there are a lot of recommendation systems that already exist. So those recommendation systems take for input the preferences, and they recommend you the artworks that you should see in the museum. Problems with those systems is that most of the time they do not propose you the pass in the museum for seeing those artworks, and if they propose you some pass, it's absolutely not optimal. So there is no guarantee of optimality with a recommendation system. And the last topic, the last domain in which this problem has already been addressed is in transportation problems. So the name of the problem is orienteering problem, and the encoding of orienteering problem has already been used for personalizing city visits. But the problem with passing to museums is that with the number of artworks, if the number of artworks is quite large, like 30,000 artworks in the Louvre, then the orienteering on problem does not apply because the encoding is quadratic in the number of artwork. So we need to find another solution for large museums. So the agenda will be the following one. So first I will present you our modeling of the museum visits problem. Then I will show you 2 approaches that we have defined, one which is a planning approach and the second one which is a constraint approach. Then I will go through experimental results and conclude on this work. So first, we have to represent a museum. So we have decided to use a graph to represent the museum topology. So what do you have in a museum? You have rooms. So rooms will be the nodes of the graphs. Then you need to connect rooms one to each other. So this will be the alleys or the corridors in the museum. And each of the alleys will be labeled by the time to go from one room to another. So in my example, to go from room 1 to room 2, you need 5 time units. Just note that the arcs are oriented because there might be some flow direction in the museum. We have a subset of entrances in the museum, so we have rooms that will be labeled as entrance and some rooms that will be labeled as exit of the museums. So now the museum visit instance problem is the following one. So we need the museum topology, which is a museum graph that I've just presented to you. Then we will need some artworks. So we have a finite set of artworks. And we need to know in which room the artworks are located. So we'll have a function that tells us that. To each artwork, we will associate a score or utility that represents the satisfaction that the artwork will bring to the visitor. So on the example, you can see that the artwork P2 is the one that brings the most satisfaction to the user. Then we have P3, and then we have P1. And finally, to each artwork, we need to know how much time the visitor will need to visit the artwork. So this is, again, a function that tells for each artwork the time in time units that will be needed for the user to visit them. And the problem, the last parameter of the problem is the maximum duration the visitor wants to spend in the museum. So this is a parameter Tmax. So in the example, it's 15. And it tells us that the visitor does not want to spend more than 15 time units in the museum. What is the solution of this problem, to this problem? So a solution is composed of two things. The first thing is a walk, and the second thing is a subset of artworks that will be the selected one. So the walk corresponds to the path that you will have to follow in the museum to see all the artworks, and the subset of artworks will be the ones that will be selected for you to best match your preferences. So we have a few constraints of the solution. So the walk must be well formed. You have to begin at some entrance, you have to finish at some exit, and the room must be connected. Then, if an artwork is selected, then the path must include the room where the actor really is. And finally, the time constraints have to be respected. And when we have a solution, we will associate to the solution a score, which is a function that basically sums the utilities of the different artworks that are selected. So, we just have to sum up the utilities of the artworks. So, on the example, we can have a first solution. So, the path will be to go from room 1 to room 2, and the selected artwork will be just P1. So, you can check that the time constraint is respected. And the score to this solution is the utility of P1, which is the only selected artwork in this solution, which is equals to 5. A second solution will be the following one, so S1. So this time the path is the same. Enter in room 1 and exit in room 2. This time the selected artworks are P1 and P3. And you can still check that the time constraint is satisfied. And this time the score is greater, it's 16. And I'll let you check that this is the best solution that we can get for this example. So if we describe the museum decision problem as the following one, so given a museum visit instance problem and an integer u, is there a score is there a solution with a score greater than or equal to u? So this is a museum decision problem, and we have shown that this problem is NP-complete. So now that we have presented the problem, I'm going to show you two different approaches to solve this problem. So first one is a planning approach. So classically, we have defined the planning approach into a domain specification and problem definition. So for the domain specification, we really require numerical fluence. Then we can define two types, one for room, one for artwork. We have a few predicates that will indicate if the visitor is present in some room, if an artwork is located in a room or not, if the artwork has been seen, and if two rooms are connected. We have a few functions. So the two first ones are fluents that will vary in the resolution. So total utility will correspond to the actual score of the solution, and remaining time will correspond to the remaining time, the time still remaining to visit or to move. Then we have our three functions that represent respectively the utility, the time to look at some artwork, and the time to move from one room to another. We have two basic actions. The first one is move. So move allows the visitor to move from one room to another. So precondition is that the visitor must be in the first room and that the two rooms are connected, and that there is still time to do this action. So there is still time to move from this first room to the other one. The effect is that the visitor is no longer in the first room but in the second, and the remaining time is decreased. Second action is to look at some artwork. So the precondition is that the artwork must be really located in the room, the visitor must be in the room as well, and the remaining time must also be sufficient for the visitor to visit the artwork. And the effect of for this action is that the remaining time is decreased, and this time the total utility of the solution is increased with the utility of the artwork that has been seen. So this was for the domain specification, and if we go through the problem definition, so if I take my toy example, so there's nothing particularly difficult in that, so we have to model our different objects, so the rooms and the artworks. The goal is for the visitor to be at the end in the exit while maximizing the total utility of the visit. And of course, in the initialization, you make the visitor start at the entrance of the museum. So now I'm going to detail you the constraints approach. So in the constraints approach, we have one constant that will be very important to us, which is the maximum number of moves that the visitor will need to do the visit in the museum. So I will come back on that constant later. But once we have these constants, we have 3 sets of variables. So those are Boolean variables. The first set of Boolean variables indicate if an artwork belongs to the selected ones, so the ones that the visitor will have to see in the visit. We have Boolean variables that will indicate if the visitor has seen the artwork and at which step he has seen it. And we have some Boolean variables to indicate which arc. So, for example, at step K, the visitor goes from room I to room J. And once we have those variables, the constraints are the following ones. So the objectives function is to maximize utility of the visit. Then we have big constraints that indicate that the maximum amount of time have to be respected. So this is the pseudo-Boolean constraint. And the other constraints are just clauses. So I'm not going through details, but constraints to say that there is one alley per step, constraint to say that the work must be well formed, constraints cannot read, so artworks must be in corresponding rooms, we have to start at some entrance and to exit at some exits, and we have to do some corresponding between our 2 sets of variables. So in the constraint approach, the number of variables and the number of constraints are this time mainly linear in the number of artworks, which is an improvement comparing to the orienteering problem encoding that I told you in the introduction. But the number is very dependent on the constant K I told you about, which is the maximum number of moves that the visitor will have to do in his visit. So we need to find a very good upper bound of this constant because this will have a big implication of the constraints encoding. So we have proposed 2 methods in the paper to find a good upper bound, and one of these methods is to find a shortest complete walk of the museum. So yeah, I will let you read the paper for details about that, but to find a good upper bound might be NPR'd. So now through experimental results. So the next step now is to define some benchmarks because there is no benchmarks at the moment for these problems. So we have chosen 2 museums. First one is Palais des Beaux-Arts in Lille and second one is National Gallery. And in the tab you have the different features of those museums. So the main thing is that the Palais des Beaux-Arts is quite small museum, so with a number of rooms which is about 50 and the number of artworks is about 500. And National Gallery is a much bigger museum, and we have almost 2,000 artworks in this museum. So these are the graphs representing the museum. So on the left you have the Palais des Beaux-Arts and on the right you have National Gallery. So you cannot see, but this just gives you the feeling about these 2 museums. So we wanted to define benchmarks with different utility distribution, and the question we ask ourselves about this utility distribution is the following one. Can a high utility artwork be replaced by any other one in the museum? And so we tried to define three utility distributions that give a different answer to these questions. So the first distribution is uniform. So in this case, any high utility artwork can be replaced by any other one. You can find another artwork quite easily. In the second one, which is a Fibonacci-based distribution, it will be quite hard to replace any high utility artwork by another. And in the Luby-based distribution, it will be quasi impossible to replace masterpieces by any other artwork. Then we wanted to model the visitor profile, and specifically the interesting artworks or not interesting artworks. So we fixed the percentage of artworks that do not interest the visitor at all, or the visitor, and we also fixed the percentage of the artworks that will have the highest utility score. And so, for example, there are some benchmarks where we say that 10% of the high artworks do not interest the visitor at all. And then we have different times that are very important in the benchmarks. So we suppose that the higher the more interesting the artwork is, the more time the user will spend in front of it. Then we have two durations, which are the duration that the visitor will need to go from rooms to another, and the time that the visitor will need to look at some artworks. And we use different ratios between those two durations. And finally, we took some different values for the maximum amount of time that the visitor wants to spend in museum, going from 15 to 300 units of time units. So this gives us 480 benchmarks for each museum, so 2 museums, which makes 960 benchmarks for museums. And those benchmarks are available on the website, so you're free to download them and use them if you want. So what are now the experimental results? So we used 4 solvers, Cplex, which is the well-known mixed integer solver, CLASP and SAT4J, which are pseudo-Boolean solver, and for the planning approach, we use LPG. And the thing is that all optimal solutions were found by Cplex. SAT4J and CLASP had quite good behavior on most of on the instances. I could find plans for most of them. And LPG, we gave very good results and found a plan for all the benchmarks. And so we tried to understand why LPG was so good. And we think that's because LPG first look for low-cost plans. And so by looking first for low-cost plans, it can have very good scores very quickly. And so noticing that, we have defined a dedicated solver, PMV, which is based on SAT4J, and that will look for plans with incremental lengths. And actually, PMV was able to find a plan for every bench as well. And so finding a solution is a good thing, but we need to find a good solution. So we had to check the quality of the solutions that were found. And so on the left, you have the solvers that found optimal solution. Then the next column shows the best solution, and the more you go on the right, the less the less good are the solutions. And so you can see that PMV, which is the yellow solver, was very good at finding good solutions for the Palais des Beaux-Arts. And we have quite the same behavior for the National Gallery problem. So what about those results? So you can say that optimal solutions were found, but only for short times visits. So for all benches with a Tmax that was not very high, we could find an optimal solution. And Cplex was the one who found all the optimal solution. CLASP and SAT4J had quite good results with Palais des Beaux-Arts, but when it comes to large museums, they were not able to find very good results. LPG and PMV could find optimal, so they could not prove that it was optimal, but they found the optimal solution for both museums, not all the bench, but for many benches of the 2 museums. But when we come to larger Tmax, so the higher the time we want to spend in the museum, the harder it is to find a good solution. But we can always find non-optimal solution, and when it comes to non-optimal solution, LPG and PMV are the ones who give the best results, and PMV actually is the one that gives the best results. So I will now conclude on this work. So what we wanted to do, so we have defined the museum visit problems and give two approaches, a planning one and a constraints one. We have improved the encoding scheme. So the one that was used before for museum was a quadratic one in the number of artworks, and we have improved it. So now the encoding on the constraint side is now linear in the number of artworks. We have generated a set of benchmarks for real museums. So as I said, there are no benchmarks that you can use if you want to work on this problem. We showed that optimal solutions can be found in specific cases, so for short time visits, and CPLEX was very good at finding one. And we had very good results with LPG and PMV. So the good results of LPG shows us that domain-independent planners are very good about rapid prototyping. And the very good results of PMV, the excellent results of PMV shows us that the right way to consider this museum problem is both as a planning problem and a constraint problem. Why? Because PMV uses a planning approach, searching first for low-cost plans, but still using the constraints on coding to find the good solution. So this is probably, for this problem at least, the right way to consider it. So about future works, we have an ongoing partnership with the museum, and we have already implemented a prototype of such a tool. The prototype is called Takeaway. We want now to have a more accurate visitor profile. So if we have a partnership with the museum, we will probably get some true information and some statistics about visitors and what they want to see in the museum. So this will give us more accurate utilities and visitors. And we would like to relax the independence assumption for summing utilities. So we would like to represent the fact that maybe if we have if we visit two artworks together, it will bring more satisfaction to the user than just adding the utilities of the two artworks independently. And as well, there is most of the time in the museum, so the last perspective is that most of the time in the museum, artworks are not put randomly into rooms. They have something in common, which can be the topic, the periods in which they were made, or something like that. So in most museums, this must be something that may be taken into account, and I'm sure that we can improve our algorithms, and especially with PMV. So thank you for your attention, and I will now answer your questions.